All right, so we finished up chapter 2 talking about the TCP/IP model. So pretty cool stuff, right? You're going to notice that chapter 1, chapter 2, chapter 3, and maybe chapter 4. Let's take a look at chapter 4. I mean, why say maybe? And chapter 4 are going to be a lot of concepts. This is normal with the CCNA. Do not get an idea that your entire time is going to be theory. Unfortunately, the part of the course has to start off this way because there's lots of things that we need to understand. You know, when we put on an IP address, there's things happening in the background. The second we do a no shut on that interface, things happen. So it's the best to know what's happening in the background. We can't really troubleshoot something if we don't really understand what we're trying to accomplish when we do it. So there's a lot of theory in the beginning. And even when we get into starting to configure the routers and stuff like that and the switches, you start to realize that there's still theory with it, but it's kind of a 50-50 thing going on. You're spending a lot of time on the equipment, but you're also going back to go through those theories and so on and so on. But nonetheless, TCP/IP is a suite. It's a stack of protocols. It's a mixture of IP protocol and TCP protocol. So what we talked about earlier was the fact that when we were going through the OSI model, how TCP was guaranteed and UDP was not guaranteed. It was just best effort. And up here you can see it says TCP is a protocol stack used for communication between nodes. Now, it's not the only protocol out there that can be used to communicate between nodes. And what are nodes? That's right, nodes are PCs, just like we were talking about before. And TCP is the concept of having guaranteed delivery, which means whoever you're communicating with, they're going to be communicating behind the scenes along with the transformation of the data to make sure that each one is getting each piece of data. So let's take a look at PC1 here. And PC2. As PC1 is sending data over to PC2, PC2 is going to receive that data coming in on its interface, and then PC2 is going to send a message back saying, hey dude, I got it. And that's just pretty much it. And they'll keep going back and forth for every piece of data that they keep sending to each other. They're going to acknowledge that they got that piece of data. And this is how this guaranteed delivery works. Now, UDP is pretty much PC1 is going to take the information and send it out of his interface, and he's not expecting anything back. Now remember the important aspect of the OSI model. What's really the main key factor of why we learn the OSI model? Yes, we learn it as a means of learning how to communicate and so on and so on. But the main thing that we're learning here is the building of the headers. That's really the most crucial aspect. As the PC1 is building something or is trying to send data, he's going to build that information. Now, what does that mean? That means I'm going to have my data here. Here's my data. If I have port information, my layer 4 goes here. That might, we'll say just port 33. Just pick whatever port number. On top of that, that layer 3 header is going to have the source IP and the destination IP. And then on top of this, the layer 2 is going to have its header information. And it's going to have the source MAC and the destination MAC. Now, when we put something in front of the real data, we like to call the data the payload. This is a term I don't use often as far as the course is concerned, or just in general. I feel that communicating with you or anyone, there's certain words that I use and I don't try to use those words. just because I'm teaching. But the payload is just whatever you're sending. To me, that's just data. I mean, all of this is data, but the bottom line is when I have this setup here, the data will be the payload. The payload is what we're trying to get, the real information we're trying to get from PC1 to PC2. We have to understand that once the data has information in front of it, which you have to understand this as well, the data has to have something in front of it. Because if this information is in here, like I showed you in the OSI model, the data is not going to go anywhere anyway. If we did not have source and destination IP addresses, source and destination MAC, the data just won't go anywhere. If PC2 received this data coming in here with no other information, PC2 is going to say, well, okay, but I have no idea if that's for me, so I don't really care about it. Only when PC2 sees that the information is for him, he will accept that information. Now, it's still coming into the network card. Don't get me wrong. It's not like if you just block all this data and you're not going to be eating up the bandwidth of your network card. Now, when I say the bandwidth, really we're talking about the bandwidth of the network card as it's going across the wire. The network card has its bandwidth itself, but I'm talking about as the wire is coming in. I mean, as the data is coming across the wire. So, if we have a bandwidth of 100 megabits per second, and this is being filled up with data and your bandwidth is maxed, they might be dropping 90% of the data that's coming in there, but the bandwidth is still used. Does that make sense? I mean, it still has to get there in order for it to get dropped. And you can think of it as a traffic jam. You got thousands of cars going on this one highway, and only 10% of that is allowed to go through. Well, the traffic is still backed up. Your bandwidth is still used. So, because of this, we need this information in order to figure out where it's going and figuring out if that data belongs to me. Now, when we put something in front of a data, we call it encapsulation. We call it this because of the fact that it's second I put a layer 4 information on here, I can't see the data anymore. This is all I can see. Once I put layer 3 information on here, I'm not looking at the layer 4 or the data. I'm looking at this. Once I put this layer 2 information on here, I'm not looking at the layer 3 information. I'm looking at the layer 2. The reason why we call it encapsulation, look at it like this. It's encapsulated because you're not going to pay attention to layer 3 or 4 or data. You don't know what's behind there until you decide from the layer 2's perspective, the layer 2 header, that this belongs to you. So if this is going to a destination MAC address of AAAA, and this PC down here, MAC address is BBBB, when that data comes into this network card, PC1 is going to look at it and say, well, wait a minute. I'm looking at the destination MAC here of the layer 2 information, the layer 2 header, and it doesn't belong to me. Well, if it doesn't belong to me, what am I going to do with it? I'm going to drop it. Why would I go any further? That's the concept of encapsulation. We have taken the data and we have encapsulated that data with layer 4 information. Now, if we encapsulated that with layer 4 information, now we have this data that's literally is going to be encapsulated by layer 3 information. And if that's the case, then we're going to have this data that's encapsulated by layer 2 information. And then, of course, this whole piece of data is what's going to go into the PC. Now, if the PC2 sees that the destination is BBBB, then PC1 will say, oh, well, that's my MAC address. It's for me. So I'm going to go ahead and strip off the layer 2 information, look at layer 3. Then I'm going to look at the what? Destination MAC address. I'm sorry, destination IP address. And if that destination IP address belongs to me, then I will strip that off and look at the layer 4 information. So anyway down the line, this data will be lost or dropped if it doesn't belong to them. So what does this mean? With TCP, we are sending all this data back and forth and guaranteeing the data. However, with UDP, that data gets sent out, which means I'm going to take my data, I'm going to build my layer 3 information, I'm going to build my layer 2 information. Yeah, we didn't have layer 4 in there in that time. Remember, if we're not going to use the information, there's nothing to put in there, right? And we're going to just send this out the interface. Now, because PC1, or PC2, sorry, because PC2 is connected on the other side of this link, he will get that information. But PC1 has no idea if PC2 got it. I mean, this wire could go somewhere else. PC1 doesn't know. I mean, what if PC1 was sitting on a switch? If PC1 was sitting on a switch, and so was PC2, PC1 just knows he sends it out. That's it. He has no idea he's connected to a switch, nor does he care. He just knows that he has an uplink, and that's the active interface that data needs to go out of. That's all he knows, and that's all he cares about. So UDP we like to call best effort delivery. There's no guarantee. Now, the real lesson of this, though, is really what TCP does. Now, we saw this before looking at the TCP IP protocol suite. And when we look at this and we compare it to the actual OSI model, we got the data link sitting here. We got the network sitting here. Let's move this over here. We got the data link. We got the network, and we got the transport. Now, at the transport layer of the OSI model is where TCP and UDP sits for our TCP IP protocol suite. Now, remember, this is a suite of protocols. This is not a model that we're looking at here. This is actually the TCP IP protocol suite. So, of course, this portion, these protocols of the TCP IP suite, the TCP and UDP, is just showing you what layer of the OSI model it works at. And it's going to be the transport layer. Now, based on that, let's find out how TCP initiates and starts communication between two PCs. When PC1 wants to set up a TCP communication, which means if an application like Firefox decides that he wants to, he, she, or it, that Firefox itself wants to set up or get some data from a web server. Now, once this happens, before data can really come from PC1 and 2, we have to have a TCP three-way handshake established first. Now, this is very important to understand because the real data is what Firefox is going to be receiving from the server. If that's the case, I need to have this method of setting up communication first before I get any data, which means if we cannot get through the three-way handshake first, we would never be able to start sending data. And what's the three-way handshake? Well, we have two types. We have two types of systems we're dealing here: the client and the server. So in a TCP session, whoever initiates the actual communication, they're going to send out what is called a sing message. S-Y-N, I might have said it wrong, but send message, sorry. I just said sing, but send message. Now this send message is saying, I'm trying to synchronize with you. And because PC1 is the one who sent out the original send message, he becomes the TCP client. And the person he's trying, whoever is receiving this send message, which is the PC that PC1 is trying to communicate with becomes a server. All because this dude initiated it. So he's the client. So now he becomes a server. Now, when this send message goes over to PC2, PC2 is going to receive it. He's going to look at that send message. Now, remember, everyone, there's certain, when we're communicating, there's certain information that we have to have. Remember, we might be sending out a send message, but this is still a message. It's still data. So what else do we still need in there? Well, we need the layer 3 information, source and destination IP. You're going to have those headers on there, and you're going to have the layer 2, source and MAC address in this message somewhere. Now, if you looked at Wireshark, you would definitely see it. You would see the TCP information sitting here, and you will see the layer 3 information, the layer 2 information. So remember, this is how PCs are getting the data, the information that they need, all from the headers.